SwayamPrabha. Digital India. Educated India.
So, good morning students, welcome to the NPTEL course on architectural acoustics. This course is the as you know, it is divided into 8 week and we are in the second week. Second week, lecture number 8, the indoor acoustics and reflection and absorption of sound. This week lecture was started with Dr. Shumana Gupta and the room acoustics is initiated. In that room acoustics, we came to know some principles and some observations of sound and the behavior of the sound in the interior. Today, we will going to deal with the reflection and the absorption, which are the two major phenomena in indoor acoustics. So, we have some learning objective in that we will try to classify and compare the behavior of the sound, how in the behavior of the sound in the enclosed space we will going to behave and what is the follow up classification of that. We are also going to know about the absorption and the reflection and relate that these two phenomena in a particular room acoustics domain. We will derive some concept and from that concept our major goal will be the derivation or the understanding of sound absorption coefficient. So, let us start with the some phenomena. If you see the general behavior of the acoustics in the sound in the interior, the propagation of sound where it is strike to a boundary element or the boundary surface, because you know the indoor is actually the closed by 6 surfaces in a particular space is closed by 6 surfaces. So, when it strike in some of the boundary surfaces, there are typical phenomena occur. The first one is reflection, the second one is called diffusion, the third one is the absorption and the fourth one is transmission of sound. So, all those 4 phenomena are very important in the domain of the understanding of the room acoustics. So, we will discuss one after one. I know that Dr. Gupta has already taught about the reflection, diffusion and all, but we will just go in a brief manner and we will try to visualize the phenomena in a different way. The reflection of sound is actually when a particular sound strike in a boundary surface and it is revert back. So, it will go to a particular direction and this direction is follow some systematic rule which is a reflection law of reflection, which is very similar to the law of reflection for the optics. So, if there is a reflection, so the amount of sound energy is incident on a particular surface will reflected back or revert back. So, the almost no decay will occur in the sound energy, almost no decay, it will be some decay will occur, but it will be very less. So, by this phenomena when there is a reflection and there is a regular reflection in a symmetrical or the systematic way, then the sound density, the energy density in a room will be remain almost unchanged. And another important thing is that this energy density will fluctuate over a wide range. So, suppose you take a particular corner of a room and there is sound energy density, another corner there may be some different density and this fluctuation having a wide range of minima maximum. As you already know, if there is a concave surface, it will disperse, if it is a convex surface, it will submerge or kind of the converge in a particular point which is called a hot spot. So, those are the typical phenomena for the reflection. Now, for the diffusion, It will happen if suppose if there is a beam that projected out, or maybe in a wall there are some kind of the curtains. So, in this case, suppose I take a energy sound path, when the sound is incident on this beam, there will be some kind of diffraction. So, there will be it will obey the reflection of sound, the law of reflection of sound, but by virtue of the change of order of the dimension, or maybe there are heavy folds, it will going to diffract. So, if there is any such phenomena or any such the boundary conditions are of different geometrical shape, it may the regular reflection may lead to the homogeneous diffusion. So, let us go to the next slide. So, the diffusion is in case of the diffusion, most of the sound is revert back after striking the surface, which is very regular like the reflection, but it will be a diffracted back or the revert back in a divergent path in a irregular manner, which is the one of the significant difference between the reflection and refraction. The sound energy density of the room will remain unchanged, because there is almost no loss, it is something like reflection only, but a uniform sound density will be observed, and the maxima minima in the various point on the building or the space will be a smaller range. So, you will get a almost uniform sound level all over the room. The next one is absorption. The absorption criteria is again a very interesting criteria, and here by virtue of some kind of surface boundary conditions, or maybe there is some in the ceiling there are some kind of the regular cavities, or maybe there are some very fibrous material. So, depending upon this particular surface conditions, the sound energy will entrapped. There may be a reflection, but in some of the because of the dimension of this particular recess, it will be entrapped. And due to that, the revert back of the sound path or the sound energy will not going to happen, or there may be a very minimum amount of energy will revert back or reflected back. So, this is a typical phenomena of the absorption of the material or absorption of the sound in interior. And again, let us go back to the PowerPoint presentation. So, the most of the sound energy decay during the after the striking of the boundary surface, because of some kind of physics behind it, or some kind of the frictional loss, or some kind of the mechanical loss. The very small amount of energy will revert back to the space. I have just now discussed that one, and the sound energy density of the room will be rapidly decreased, because nothing has to be come again into the space. So, most of the sound energy which was fallen upon a particular surface, that will going to absorb by the surface. So, there will be no such the reflection back of the energy. The fourth, what we have discussed as a part of the behavior of the sound in the interior is the transmission. And there are two type of transmission, one is called the airborne sound transmission and one called the structure bound sound transmission. So, in the airborne and structure bound sound transmission, we will going to have, suppose this is a particular wall, brick wall or maybe any wall of any such material, and this is the source room and this is the receiving room, and there is a sound which is a high level sound incident on this particular partition wall between these two rooms. And when we will see the propagation of the sound, and when it travels by transmission by between this particular wall, which is the partition wall, the sound level will going to drop, and the propagation of sound or the amplitude of the sound will be little low. And this is the airborne sound transmission. Very similarly, there may be a structure bound sound transmission, because maybe this is a concrete slab and there is some kind of a machine or some object which creates some kind of a vibration and sound, and the sound will travel through this particular surface itself and propagate and enter into the other receiving room or the other room, and this is called the structure bound sound transmission. So, in structure bound sound transmission and the airborne sound transmission has two very different approach. I mean, when we actually deal with the stoppage of that particular transmission sound, and we will discuss in the latter part of our discussion. And the structure bound sound. So, in case of the airborne sound, the sound energy penetrate from the boundary element and it will reaches to the other part of the thing, and it will be created by some kind of a vibration or some kind of the resonating effect. Whereas, in the structure bound sound, sound will travel through the material itself, the envelope material of the building or the room itself, and it will, when it will propagate, there will be gradual loss of the sound energy and it will propagate from one point to the other point. And how much the loss will be occur, it will be depend upon the what is the resistivity of the material against the sound path. So, let us go to the next phase of my presentation, where I will now discuss the reflection and the absorption. Suppose in this yellow stick is suppose a surface, and there is a incident sound ray or the sound energy is fall upon that particular surface. There will be a reflection and there will be some absorption. So, I can say that the incident energy or incident amount of energy must be equal to the reflection energy and plus the absorption energy, and there will be some 2 or 3 cases. One case is suppose the both are same. So, it is a non-reflective or non-absorptive kind of a surface, and when the reflection is much higher than the absorption, I say it is a reflective surface, and when the reflection is much less with respect to the absorption, then it is a absorptive surface. So, in this figure what we have shown is that it is a reflective surface and the absorption part is quite less with respect to the reflection part, and the surfaces which is very popularly known for or very actively participate in the reflection is the hard plaster surface, exposed concrete surface, metal surface or stone cladding, those kind of the very hard surface. In the other hand, the absorption is where the amount of reflection is less and the amount of absorption is more by virtue of some the nature of the surface material. And I have shown here in this particular figure, you see the blue line which is a reflection line is quite smaller with respect to the dotted red line which is absorption, and absorptive surfaces are quite soft surface with respect to reflective. It is soft fabric, soft panels, surface with various irregular or regular recesses, both all are act as a absorptive surface, and they have different further classification also. So, in general, the absorptive surface material or the absorptive material can act like, I mean the way it actually handle the absorb the energy is finally translated to the mechanical or the heat energy, which energy is actually sound energy is absorbed, which is going to the translated or the transform to a mechanical or heat energy, and by how it will actually transform the heat or mechanical energy. From that point of view, there are three classification of the sound absorptive material. One called frictional absorber, one is called vibrating absorber, another is called resonating kind of absorber. So, in the next week, Dr. Shumana Gupta will tell you in detail what is the various significant difference between them and how and where to adopt those particular absorber for better sound environment. Now, let us, when we talk about this absorber, let us find out some coefficient or some physical quantity or parameter from where I can actually measure and actually compare between two absorber. So, that is why a non-dimensional quantity called absorption coefficient or popularly called as a sound absorption coefficient is thought of. And the sound absorption coefficient is defined as the ratio of amount of sound energy that is incident on a particular surface and the amount of sound energy that is going to absorbed by a particular surface. So, actually it is absorption by the incident energy. So, as I know the incident energy is equal to the the reflection plus the absorption. So, definitely this absorption will be quite little less with respect to the incident. So, the value of the absorption coefficient will lie between not more than 1, I mean lie between 0 to 1, that fluctuate between the 0 to 1. So, suppose this is a panel in this particular slide you see, and there is incident energy of I which fall upon a particular area, suppose a unit area of 1 meter square, and there is the reflection which is R over here, and there is the absorption of A. So, by definition the absorption coefficient is A by I, and this coefficient is going to, suppose if I get some kind of the sound intensity, suppose the initial incident intensity is 0.1 watt per meter square, and after reflection a very feeble amount of 0.006 watt per meter square is reflected back to the room. So, 0.004 watt per meter square is absorbed. So, I can say the absorption coefficient of this particular panel is 0.4, because A by I is 0.004 by 0.01. So, suppose now I can write the like I watt per meter square. This is just from the last slide. If I say if the initial incident energy is I watt per meter square, the particular the intensity, and after reflection let us have this reflection coefficient as alpha. So, alpha equal to A by I. So, then the A is equal to I alpha times I. So, that much is absorbed, alpha times I. So, what remain with me in the room after the reflection is I minus alpha times I, because alpha times I is actually absorbed. So, this much amount of left with me in the after the reflection. So, the reflection will be 1 minus alpha whole into I. Now, this alpha, the value of alpha or maybe the absorption coefficient alpha is depend upon two quantity or two phenomena or two parameter. The one is angle of incident and another one is the frequency. So, as I have already told you that this particular angle of incident will be equal to the angle of reflection. So, this reflection law of the optics will follow also in the sound. So, we will get different amount of alpha values for different amount angle of reflection. Suppose if I test a particular panel with theta 1 angle, I may get a alpha 1 for that. So, the absorption versus the incident is the ratio is alpha 1. Now, suppose in the second test I change the value of the angle of incident to alpha 2, and alpha 2 is less than suppose alpha 1 or maybe more than alpha 1 also, I am sorry, the less than theta 1 or the less than more than theta 2, then suppose in case of the second I am getting a absorption coefficient of alpha 2. So, I have to take a particular value, I cannot actually go for only alpha 1 or maybe a specific value. So, I need a average. So, I will do this particular experiment for so many times and maybe n times, and I will add up and then finally find out what is the average, and this average is known as depicted as alpha bar, and it is known as the random incident sound absorption coefficient, because it is based on the first parameter, that is the angle of incidence, the alpha values. So, I am taking the average of that particular alpha and the random average has been taken. Now, second is consideration is it is also depend upon frequency. So, if I change the frequency from some maybe one octave to the other octave, the value of alpha will also going to change. So, how can I handle that one? So, we bring another kind of a coefficient called the noise reduction coefficient, which is again a average kind of a thing from the alpha or the sound absorption coefficient. So, what we did over here is that this average random coefficient or the random incident absorption coefficient, which is alpha bar, is calculated for 4 selected octave band frequencies 250, 500, 1000 and 2000 hertz. Because this middle band of the frequency 250, 500, 1000 and 200 is the most used frequency in our normal environment for any kind of speech, music and all. And we will take the average of that. So, I have written down that 1/4 of those 4 random alpha values, and it will be actually expressed nearest multiple of 0.05, and this is called the noise reduction coefficient of any absorptive panel, and that is the end of it, because this particular NRC value is actually published in the material information brochure. So, if you purchase any material and if you want to know what is actually it will behave as a absorber, you must read the NRC value of that. So, if you see the NRC value is little high or very low, so you can say it is a good absorber or a not so good absorber or a reflector. So, and this NRC value will be actually taken for any kind of calculation. We may say in our discussion or sometimes in our write up that it is sound absorption coefficient, but actually it means the NRC value of the panel or the surface. So, there are this kind of 4 band has taken, and we can plot this 4 different frequencies, the different sound absorption coefficient with respect to this 4 middle band of the frequency, octave band frequency, and we can get the average value of that 1/4 of some of those, and can say that that is the NRC value of the material. Now, let us a small example. I have just put in some values 250 for that is 0.75, 78 for 500, 0.83 is for the 1000 and 0.85. So, the average of these 4 is actually you see this 0.8025. So, by definition I have to round up by 0.05. So, the NRC value will be 0.08. Now, the concept of this particular absorption and how it will be actually relate to a certain other the unit of absorption or so. As we remember, or we have already discussed this, the value of alpha, that is coefficient is unitless. So, suppose I have a area of a panel which is having 10 meter square of area, and this 10 meter square of area is having the alpha value of 0.4. So, I can say that if I the incident energy density is 0.1 watt per meter square, it will reflect back almost 0.004 and I am sorry reflect back 0.006 and absorb 0.004. So, the total absorption is 0.004 watt per meter square into 10, that means 0.0 watt. So, the total reflection for this particular surface is 0.06 watt or so. Very similarly, I take another surface which is 8 meter square of area and its alpha value is 0.5, and very similarly I can say that the absorption of this area is 0.005 into 8, which is the area. So, 0.04. So, this 0.04, this particular wattage or the amount of the energy that is absorbed can also be found out by multiplying this 8 into 0.5 by S alpha. So, this 0.4 4, and this is S alpha for this is also going to be 4. So, I can say that this 0.04 and this is also a 0.04, the total absorption for both the cases are almost equal, and these two are going to have the equivalency of 0.4 as S into alpha. So, we can say from this particular slide, or you can actually deduct or conclude that I can actually multiply the area and the alpha value of that particular surface, and I can actually say this much amount of proportional amount of energy can be absorbed. So, now let us see that is there is any such material which is having alpha value of 1, and what does it mean? Alpha value of 1 means it is almost everything is absorbed, nothing is going to reflect it back. See, a open window is something like that, because in an open window if there is some incident energy, almost all the energy is actually absorbed. The full absorption is going to happen and there will be no reflection, and by virtue of that the alpha value is going to be 1, because A and the I will be equal. So, suppose I have again a panel of 10 meter square and alpha value of that panel is 0.4. So, the S alpha product is 4. So, I can say that it is equivalent to a open window which is having a 4 meter square of the area, because this 4 meter square of the area which is having the alpha value of 1, because it is open window, it is give me the same S alpha product. Of course, I have to assume that the rest of the area or the rest of the panel is fully reflective. So, everything is going back. So, very similarly, suppose there are two such panel, one is green panel which is having the S1, the surface 1 is 12 meter square and alpha is 0.4. So, that, and another is suppose S2 which is a purple color, little smaller in area 4 meter square and alpha 2 of that is 0.3. So, the sum of both the S alpha product is 6. So, I can say very well from the earlier concept, this 6 is going to be like a 6 meter square of the open window area, rest 10 meter square of the area which is the other part of this particular wall is fully reflective. So, what I mean to say from this slide is that this S alpha product is related to a open window. So, it is equivalent to how much proportional area of the open window, I am just comparing that, and this particular open window concept came to in a way, and it's actually initially it was called as open window unit OWU or meter square Sabin. Meter square Sabin, because the physicist, the American physicist W.C. Sabin, he has contributed a lot in the area of the reverberation and this particular acoustical physics. For that to regards and for his particular acknowledge for his particular work, this absorption coefficient multiplied by the corresponding area is called as meter square Sabin. So, there are some list of material which I have taken from some one book which is I have given in the reference also. So, and the absorption coefficient of those materials are listed down. You see the materials which is the first, second, third row, fourth row are of very solid material, solid in the sense of very hard material and maybe a polished kind of a surface, glass, chipboard and the plastered wall, plywood panel, and you see the absorption coefficient is very low. So, it's all are act as a reflective material, reflective surface. Whereas, if you go down starting from the last, I mean the last 4 rows, if you see the curtains, then the mineral wool, then the heavy carpet and the polyurethane foam, all are having the values are the higher range values. So, those can be act as a sound absorptive surface for our this thing. So, we have furthermore there are two such mathematical equations we may think of. So, this total room absorption, suppose we have in a room 6 surfaces, 4 wall, 1 ceiling and 1 floor, and all the wall, ceiling and floor are of different acoustical material. Floor may be having carpet, the false ceiling may have some kind of acoustical treatment in the top. So, alpha 1, alpha 2, alpha 3 corresponding S 1, S 2, S 3. So, the total room absorption in meter square Sabin will be the product of the S and alphas, and if that product is called as, suppose the total absorption A, capital A, and if I divide that capital A by the total amount of the surface area available to me, interior area, then this will be the mean sound absorption of that particular area. So, that can be sometimes useful for our calculation further when you talk about the reverberation and reverberation time. So, let us take some homework for today. So, first homework is that it is not some mathematical, but you can just think of, can you differentiate between the various behavior of the sound in the enclosed space with illustration. Do some you need to draw some sketches for that. And second one, probably I have given 4 frequencies, and corresponding to that I have given 4 absorption coefficient. Of course, these absorption coefficients are of the random incident angle point of view. So, can you find out the NRC value, the noise reduction coefficient value of the absorptive panel. So, that is the end of this lecture number 8, and those are the books, those are the some of the books which we can go through for your further understanding and move for the next chapter. Thank you very much.